Alright class, this video is going to walk you through how to use the Ladybug solar radiation analysis on some conceptual masses inside of Revit. So in essence, this tool enables you to analyze and visualize the amount of solar radiation that's being collected in a given location over a given time period for a conceptual idea that you might be working on. We're going to start off using a couple of different conceptual masses in this model. I'm just going to make a 3D view here. These masses can be relatively simple, but what I would encourage you to do is to make sure that they intersect with each other. So you're sort of looking at a relatively complex shape. I'm going to hit create form, pull this box up, and then do another one that maybe isn't quite the same height. Sort of two objects here, just to start off really simply. Then we're going to go ahead and get into Dynamo right away. I've already got mine open. You can do yours under Manage tab there, and I'm going to create a new Dynamo script. The first thing to do, and you can see I've already done this here, is to install Ladybug. Under the packages, you can search for the package and search for Ladybug. And download and install it. While you're here, you can go ahead and install Honeybee. We'll be using that later on in the semester. Honeybee does radiance analysis. Ladybug uses weather data and environmental analysis to do solar, to enable some of its solar tools. The other thing that you're going to want to do is pop out to the web, and I'll put this link up on Canvas, but you can see it here. It's ladybug.tools.epw map. An EPW file is a weather file for a given location. You can see the intensity of these files varies depending upon the country that you're looking at. I'm just going to zoom in and grab one here in Charlotte. And what you can see is you can right click and it gives you a link to a file that you can pull from Energy Plus. You can also generate these using other climate tools. You can see this gives us a zip file. I'm going to open the zip file, and here are three different file types. The EPW is what we're really looking for. I'm going to move it out of this zip folder and onto my desktop so that I can find it easily. You can see I've already got it there. Okay, so now that we're set up here, basically we'll start off kind of working a little bit backwards by putting in the solar radiation component and then starting to look at what it needs to work. So basically the way that this tool works is that it needs a sky matrix, which is defined by that weather file. It basically looks at an entire year worth of weather data about the sky, so that you can analyze the amount of solar radiation that would be collected either on a given hour or a series of hours. The geometries that you're going to analyze as surfaces, it's important to note that those are surfaces. We're starting off with masses, so we're going to have to make sure we convert them into surfaces before they come in here. Point normals, which is basically the face of each location, and the number of test points that you're going to want. And as with a lot of these things, you want to keep these relatively low at first, and then you can turn them up as you go. And then that exports a solar radiation component that we'll convert into colors. We'll use some of Ladybug's color tools to generate those colors. So working backwards, let's first work on this sky matrix. So the tool that you use to generate the sky is literally called Generate Sky. And you can see it's here under Ladybug. Generate sky matrix. So that sky matrix will apply in, and now we'll work backwards, and here you can see it's looking for an EPW file. That EPW file we need to point a file path to, and we haven't used this component before, but we will be using it a lot during the rest of the semester to bring other kinds of data in. So the file path allows you to go browse and find that EPW file that we just downloaded, and I put mine on the desktop here. That reference is important. If you move the file, you'll have to update this as it goes. And you can see it opens up a component right away and starts running the sky tool to generate sky matrix to actually generate this, and it does take a couple of minutes to think through. It just does this once when you first link it up. I am realizing that while we have the sky matrix here, we haven't actually got the filtered sky matrix, which allows us to define time. And so I am going to go searching for the filtered sky matrix. Let's see if we can find it here. There it is. This is going to allow us, you can see here, to add in a bit more data. In particular, whether or not we want to include both the diffuse and direct radiation that would be collected onto the face of your building, but also the HOIs, which are the hours of the year. There are 8,759 hours in a year. You can include all 8,759, although the script will get quite sluggish if you do that. So instead, we're just going to put in a calculate HOI component, which allows us to control more specifically what we're actually looking at. By default, you can see it's looking for a month. So this is set to December 21st at noon in 0 minutes. So we want to actually say, look at a summer hour where this might be more more specifically valuable, especially here in Charlotte. So I'm going to put this at 6, meaning June. I'll leave it on the 21st, but basically move it from the winter solstice to the summer solstice. And let's change the time. Well, we can go ahead and put in a component here so that we can change the time later on. I'll set it to noon. Well, no, let's set it to a lower angle so that we can see it a little bit better. Let's set it to, say, 10 a.m. Okay, so by plugging this HOI in, it's basically saying we only want this this hour rather than all 8,759 hours coming out of the component. Okay, now to the geometry. We're going to use the category component as we have been to pull in all of the conceptual masses. So I'm just going to set this to mass. And then get all elements of that category. And we should see that we've got 2 components in there if we put a watch on it. And then we're going to use the faces from elements component to actually turn them into surfaces. And again, that's what we were looking for here. And the objects show up as our 12 surfaces on the 2 conceptual masses that we plugged in. And we do need to flatten this geometry before we start screwing around with it. So I'm just going to strip out all of the info that got us there, and then you can plug the geometries component in there. So again, a lot of these components are built into Ladybug, right? So this calculate HOI, generate sky matrix, filter sky matrix, and solar radiation are all basically built out of different components in Ladybug, giving you the maximum amount of control that you might want over how you generate these things. And the same goes for how we actually create these test points and the normals, which is another component coming out of Ladybug called generate test points. It's important when you see things like test points here to recognize that those might be different from a regular point. So the fact that it's asking for test points gives you a little bit of a clue that that there might be another component that feeds into that. So here we've got the test surfaces and number of segments as well as distance from surface, and it's going to generate the number of points and point normals. So these two really simply just kind of plug into the solar radiation component. The test surfaces are going to come out of our flatten. And then we're going to need a slider too, and you can see it's actually starting to work on those and actually run the tool, because there are some default setups inside of the number of segments and distance from surface. That default might have been kind of high. You probably want to plug either turn it over to manual so that it's not running consistently like this, or plug a slider in to the number of segments before I'm running this. I may need to pause it. Let's see. Okay, that took a couple of minutes, so please make sure, if you didn't already fall into that trap, to put a number slider on to control how many segments are actually dividing into your surfaces. Mine was set to 10 at first. I'm going to turn this down to 4. You can see the points actually showed up. And the distance from the surface, so it's going, from having 100 points to test down to 16 points to test per face. So hopefully this will run significantly quicker this time. Although with less accuracy, certainly when you go to do a final analysis, you'll want to turn it up a little bit. I might have to pause again. Okay, so at this point now, and you can tell because I keep running it on auto, that it's actually giving us data. So the data is reading out here from the set of points. On a lot of the faces of these surfaces, you're going to see that the point data, I'm mousing over and then clicking the pin here, that the point data is really similar across the entire surface. And really it's only in spots where you're getting diffuse or reflected light that you're going to get differences. And because we're only running like 4 points on each facade right now, you're not going to see a whole lot of difference. So we want to render this. We certainly could use this data to actually learn more about what's happening on particular facades and facing particular directions. You certainly could rotate some of your conceptual masses in the model to also get a sense of the relationship to the sun. The way that we're going to generate the colors is to use some of Ladybug's components that are going to give us more of a traditional gradient in terms of a heat map. So the generate colors button here, or generate colors component from Ladybug, is looking for values and then a legend parameter. And again, when you see these things that are different or unique, you can assume that they're coming out of Ladybug or coming out of whatever component you installed. And you can see this one's actually telling you that. When I mouse over it, it says Ladybug legend parameters. That means that the legend parameters, and the legend parameters are basically the colors, that the legend parameters are coming from Ladybug. And sure enough, there is the Ladybug legend parameters component. So you can work backwards from a lot of these components. And this one is looking for colors, domain, and C-type. And what we're looking for is just the Ladybug colors component. I think it's LB color range. This is where we're actually getting that set of colors that look more like our traditional heat map. And you can see, of course, we're not actually seeing the colors yet until you put the display component on, as we had been these last couple weeks. So you can put the display, surface colors, and take the colors out of this Ladybug component, and then take the geometry out of the flatten. And we can zoom out here, and we should see our colors actually rendered. And you can see at 10 o'clock here, we're getting, for some reason we're not getting color on this lower box. Oh, I know what it is. It's our usual problem where we're seeing the other geometry because it hasn't been hidden yet. So I'm going to come back and hit preview off these, and now you see the face is rendered as they should. And the key thing here that you're starting to see is the way in which these objects interact with one another, the way in which they actually cause reactions in the radiation collection on different facades. You can presume that this is the south facade, or excuse me, the south and east facade at 10 in the morning on the solstice. And then some of these other, like the north facade, is not receiving any direct light, but is getting some indirect light diffuse light from the sky. So this is a relatively precise model of a really simple set of geometries rendering the solar radiation. So as we did earlier this week, you can imagine actually coming back and appropriating and locating elements on the facade, louvers, say, or sun shading devices on the facade, or just inside of the facade to actually mitigate how much solar radiation is being collected into the building with these components. Okay, that's it for this video. Thanks.